atoms. I will then describe how one does the Hartree-Fock and Thomas-Fermi approximations of real many-body atoms. So I will go through a little bit how this is done. This is basically a semi-classical approximation. And it leads to understanding different scales in real atoms. And then finally, I will get to the universality beyond Thomas-Fermi theory. I will make conjectures about how I see this universality in real atoms. So what I will in fact do is I will make a quantitative ionization conjecture. The ionization conjecture itself is rather qualitative, but I will make a very precise generalized ionization conjecture. And then I will compare this with experimental and numerical considerations afterwards. Okay, so let me start with my motivation, which was actually related to understanding the size. So you see down here, I have the periodic table, but the periodic table of the elements, I've actually only shown the size of atoms, or rather the relative sizes of atoms. And what you're supposed to see here is that the size of different atoms, all the sizes are more or less the same. I mean, it is true as you go down the first group that they grow. And actually, I'm going to come back to exactly that phenomenon, that atoms get bigger as you go down a group in the periodic table. But radii do not change very much. I mean, I usually emphasize that if you look down here, this is uranium. And if you look up here, that's lithium. So, so lithium with 3 electrons and uranium with 92 electrons pretty much have the same size. Now, in the usual formulation of the ionization conjecture, it's not actually formulated in terms of the size of the atom. I will focus on the size, but usually since the word ionization conjecture comes from the fact that it's actually attempting to estimate the maximal negative ionization. I mean, how many electrons can I add to an atom and still have a stable atom? And it's sort of experimentally seen that it's probably just 1 or at most 2 electrons that can be added, and then an atom cannot bind any more electrons than that. So the conjecture, to make it a mathematical statement, one looks at the limit as z goes to infinity and asks whether the maximal negative ionization remains bounded in this limit. So we cannot hope to prove that it's only 1 or 2, but we can hope to prove that it doesn't grow with z. At the same time, I will add this thing about talking about the radius. I want to understand why the radius seems to be bounded above and below as z goes to infinity. And finally, one can look at the ionization energy. I mean, the energy price you have to pay to remove 1 electron from a neutral atom, and also argue that this is bounded above and below, or rather this is a conjecture. All these 3 properties are conjectures for real atoms. I will show them, discuss how much we know in the approximate models in the Hartree-Fock theory and in Thomas-Fermi theory, but I'll get to that. But before I go there, let me just discuss the meaning of an atomic radius, because often what does it mean? What do we mean when we say the radius of an atom? Now, it turns out that there is actually, to each atom, you can associate a number. This is a phenomenological fact, that you can associate a number. So this is the large atom, you can associate the big R, and here's a small atom where you can associate a little r, such that the bond distance between the 2 atoms will be R plus R. I mean, the point is that every atom, it seems, as an experimental fact, that to each atom you can associate a radius, so that when 2 atoms appear in the bond length is exactly the sum of the 2 radii. So these are these numbers have been collected by looking at lots and lots of bonds where different atoms appear, and it seems to be a rather accurate, though experimental, fact that you can define the radius of an atom in this way. I will define it later on in in a more mathematical way, but let me get to that. So,
excuse me, how precise experimentally is this atomic radius defined?
I don't know exactly how, I mean, how precise it is defined, but it's something that goes again, I mean, you see many places in the chemistry literature that...
yeah, I mean, so some elements like sulfur exist, or iron exist in many varieties. I mean, oxidation.
I don't know exactly. I mean, of course, the radius would depend on what kind of iron it is, but I think when it appears in as just the neutral iron, I think it probably is pretty accurate. I don't know exactly. I haven't looked at the experimental data. I've looked at the tables over the radii. I mean, the tables that have been collected for the radii, but I have not looked at all the compounds that have been used. Now, I should say that this has been done many times. I mean, I will show numbers done by Bragg from 1920. Slater did it again in 1964, and Pauling in particular was promoting this. So sometimes this idea of having these radii defined in this empirical way is often attributed to Pauling.
So there is a question in the chat. How do they measure the radius?
Well, actually, I think mostly they measure, of course, bond lengths. They can measure in crystals by diffraction experiments. Now, I'm not totally sure how they measure the bond lengths in molecules, but they can do it by some spectroscopic method. I mean, looking at the spectra of molecules and infer from that the bond length.
If I may have a comment, there are obvious counterexamples to this universality of atom radius. So, for example, let's take carbon in form of diamond and carbon in form of graphite. If there would be something like a universal atom radius, the bond lengths would be the same, and they are different by 5%. So,
yeah,
so this is the obvious limit of accuracy to.
Sure, there is. I mean, it's clear that it's not a very precise. It's not a very precise measure. You will also see that from these collections, like when Bragg did it, when Slater did it, when Pauling did calculated the radii, they all get somewhat different numbers, right? But since I'm not interested in the precise radius, I am actually interested in quantitative measures, but not down to a few percent. Okay, let me go through the Hamiltonian. I guess most of you know it, right? The Hamiltonian. So here I'm looking at a molecule. I have n electrons. I have m nuclei, and the nuclei are placed at the points R1 to Rm and R3. And I have nuclear charges, and the nuclear charges I think of as being integer. This is just because I would like to talk about neutral atoms, and I cannot really talk about neutral atoms since the number of electrons is an integer, unless also the sum of the nuclear charges would be an integer. So we have a kinetic energy, that's the usual -1/2 Laplacian. I'm using units where h bar is 1, the mass of the electron is 1, and the unit of electric charge is also 1. So these are Hartree units. So we have the repulsion between the electrons. The U here, the constant U, is the nuclear repulsion, and the potential V is the nuclear electron attraction. There's a minus sign in the potential, but it appears as a with a plus in the potential V. So I have a minus sign in the Hamiltonian. Okay, and the Hilbert space, as you all know, these are fermions. So the Hilbert space is the antisymmetric tensor product, and I'm including the spin value. But here I'm doing the Born-Oppenheimer approximation, meaning I think of the nuclei as having infinite mass. So the nuclear positions are parameters, and if I want to find the sort of the geometric structure of the molecule, I would minimize over the positions of the nuclei. But most of the time here, I'm actually thinking of it as a parameter. So the nuclear positions will be a parameter, and I'm interested in how the energy of the atom depends on the values of these parameters. So I'm looking at the Born-Oppenheimer curve. The ground state energy is the infimum of the spectrum of the Hamiltonian. And I can immediately define one of the quantities we had before, the ionization energy. It's simply the energy that you need to pay in order to remove one electron from a neutral atom. So to go down to a number of electrons, which is Z minus 1 from Z, right? So I will have a higher energy if I have Z minus 1 electrons. So I have to pay a price to remove one electron. And the Z here is the total nuclear charge. Okay, so let me think about what can we say about the ground state of atoms and molecules. Now, a ground state may not necessarily exist, but if it exists, when it exists, it's the eigenvector with the ground state energy being the eigenvalue. I mean, I always have an infimum of the spectrum. I may not have an eigenvalue at this point. And in fact, I'm defining the NC, the critical number of electrons, as a function of the parameters R and Z, to simply be the maximal number of electrons such that a ground state exists. Right? And then the maximal ionization is exactly this number minus Z. And it's not a very difficult statement to see that this is actually positive. I can always bind more than Z, or at least Z electrons. A property that quantity of particular interest is, of course, the density in the ground state. And the density in the ground state is the density corresponding to the wave function. So you simply integrate out n minus 1 variables. And for normalization purposes, I put an n in so that the integral over the density is equal to n. And then let me give a mathematical definition, a possible mathematical definition of the atomic radius. I call it R1. And it's simply the radius, so that outside this radius, I have exactly one electron. So it's here I'm doing it for an atom, of course. Everything else I was saying up till now was for molecules, but for the radius, I'm of course restricting to atoms. And what I'm saying is the R1, the radius R1 is defined such that the number of electrons outside the ball of radius R1 is equal to 1. Of course, you could also talk about the radius R2, and I think it depends on the type of atom, what would be the right definition for the thing that corresponds to the empirical radius that we were discussing before. But I'll get back to that in a little later when I will try to estimate this radius R1 for different atoms. Okay, so now let me go to the approximate theories. So let me first take the high-level approximate theory, the Hartree-Fock theory. There you simply restrict wave functions. I mean, the ground state can be extremely complicated. It can have an extremely complicated correlation structure. But in Hartree-Fock theory, you restrict to Slater determinants. I mean, Slater determinants are the ground states for free electron systems, but you don't have a free electron system, but you restrict to the type of wave functions that would minimize free electron systems. So you minimize over Slater determinants. So you have n orbitals psi1 up to psi n, orthonormal orbitals in L2, and you form the determinant. Yes, sorry.
So sorry, another question in the chat. What is the rate of decay of density with respect to x?
Oh, it will, I think it will be exponentially decaying, but I don't know. It may only be polynomial decay. I don't quite know, but I'm not totally sure if it's for the neutral atom. I will get to another type of decay of the density in a moment, but somebody may know exactly whether it's exponential or maybe it's only polynomial. I don't quite know.
Because Stephen Watson is remarking that if it is exponential, then you get indeed a characteristic length scale.
No, well, not really. I mean, you mean the characteristic length scale when I define the radius over here? It depends a little bit what you would call a characteristic length scale. There are many length scales in the atom. And the exponential decay, if there is any, I'm not sure there's exponential decay. I would think there may only be fast polynomial decay, but I don't know. But if there's exponential decay, this exponential decay would probably, as you think of it as a dependence of z, as z goes to infinity, it will probably be independent. I mean, it would be bounded independently of z. Whereas, as we will see, there are other characteristic length scales of the atoms that strongly depend on z. Anyway, so for the Slater determinant, when I have this, when I restrict to these wave functions that are Slater determinants of n orbitals, then when you want to calculate the expectation of the energy, I wrote it down here in the Slater determinant, it depends only on the one particle density matrix. And I wrote the one particle density matrix here. It's an operator on the one body space L2 of R3 with values in C2. And it's in fact the projection, it's the projection onto the n, the space spanned by the n orbitals. And the corresponding density is the sum of the densities of each individual orbital. Now, I'm doing a norm here because remember that each orbital takes value in C2, so you actually, but the density is a scalar function. And then when you calculate the energy, the expression is here. You have a term which is the kinetic energy. It's expressed from the one particle density. We have the potential. It's also expressed by the one particle density. The electron-electron repulsion will be the density-density interaction. This is what's called the direct term. And then there's also an exchange term, which is negative. And there was the nuclear-nuclear repulsion still. And the potential, remember, that was the attraction to the nuclei. So everything can be written in terms of this one particle density gamma. And again, I can minimize over all Slater determinants, meaning minimizing over all projections gamma. When I do this, when I minimize this expression, I get the ground state energy. From the ground state energy, and I put an HF here to emphasize that it's a Hartree-Fock theory that I'm working in. Or you can have the ionization energy defined exactly as before. Ionization energy in Hartree-Fock theory, the energy it would cost to remove one electron. And we can talk about the maximal ionization. This is the maximal n you can have bigger than z, the maximal number of electrons bigger than z you can get, and still have a minimizer for the Hartree-Fock problem, which is the minimizer of this variational principle. And finally, you can again define the atomic radius R1. Let me then go to the, we want to say, low-level theory. I mean, the simplest of all theories. That's the Thomas-Fermi theory. So in Hartree-Fock theory, everything was dependent on the one particle density matrix. Thomas-Fermi theory is the simplest of a large family of theories called density functional theories, where the energy is expressed only in terms of the density. And essentially, how do you do it? How do you get from Hartree-Fock theory to Thomas-Fermi theory? Well, one thing you do is you ignore the exchange term, right? Remember, if I go back one slide, the exchange term we had there. Right? The exchange term is, for instance, saying that if there's only one electron, it doesn't interact with itself. If there was only one electron, then the direct and exchange term would exactly cancel. An electron does not interact with itself, but for many electrons, it sort of expresses a little bit the whole that's created around each little electron, emphasizing that it does not interact with itself. Now, in Thomas-Fermi theory, you ignore the exchange term, and you replace the kinetic energy by an expression that depends only on the density. Now, how to understand this expression here? I mean, one way, which I will explain below, is semi-classically, from a more mathematical point of view. But you can also just think of it from the free Fermi gas. We know that in the free Fermi gas, the energy goes like n to the 5/3. And if you use this energy n to the 5/3 locally, you can express it as an integral rho 5/3. This is how Thomas and Fermi introduced it back in the 20s. And then the energy as a function of density will be the kinetic energy, which I got from here when I replaced things by rho. There's the interaction with from electrons and nuclei. There's no approximation there. That's the value. It depends only on the density. There's the direct term. Again, there's no exchange term because I ignored it. And finally, there's the nuclear repulsion. I see a lot of activity in the chat, but Daniel, I hope you ask questions if there are any questions.
I will. I think these are excellent comments, but not a question for you. So
okay, I'll just ignore it then for now. Okay, great. So again, just as before, there's a ground state energy. I can minimize this functional here over all densities corresponding to having n electrons, so that the integral of rho is equal to n. Right? So I can minimize this, I can get a ground state energy. When I have a ground state energy, I can calculate the ionization energy. I can again calculate the radius. This was something that was only in terms of the density. And finally, I can ask the question of the maximal ionization, meaning how much mass can the density have bigger than z in an atom or in a molecule for that matter. I mean, the integral of rho equal to n, how much bigger can that be than the total nuclear charge in order to have a minimizer for this functional. And in Thomas-Fermi theory, this number is known, it's equal to 0. Thomas-Fermi atoms cannot, or molecules cannot be negatively ionized if you have more electrons than charged, you will not have a minimizer in that case. And let me emphasize that the minimization problem and the results I have stated here were studied by Lieb and Simon in 2 papers, one on Thomas-Fermi theory and one on Hartree-Fock theory. Let me then say a little bit more about Thomas-Fermi theory, the scaling in terms of Thomas-Fermi theory, because that will be important for the universality that I will talk about. So, and I'm doing it here only for atoms. This is for simplicity, to avoid having to scale the nuclear positions as well. So, but of course, there's a very simple generalization to molecules. So if I look at the neutral atom, and I ask how does the ground state energy in Thomas-Fermi theory depend on z? Well, then it goes like a constant times z to the power 7/3. And I'll come to that later on. The density for an atom of charge z is given by a fixed function. I called it ρ1 because that the function corresponding to hydrogen, if you want, z equal to 1, and simply rescaled in this way. So there's a z squared and there's a z 1/3 x. So the atom, and here is already one characteristic scale of the Thomas-Fermi atom. The characteristic scale of the Thomas-Fermi atom is that x behaves like z to the minus 1/3. I mean, the length scale of ρ1 does not depend on z, it's order 1. So this thing here should be order 1, meaning that x is of order z to the minus 1/3. So large atoms, large Thomas-Fermi atoms seem to scale with z to the minus 1/3. So large or heavy atoms become smaller. The radius becomes smaller and it goes like z to the minus 1/3. But we'll see in a moment that the radius I talked about before, the radius 1, actually does not go to 0. And I will try to explain this. But let me just introduce one more quantity before I get to that, the Thomas-Fermi potential, which is simply the mean field potential that the electron sees. So there's the z divided by x, that's the nuclear nuclear attraction. Remember, I had a minus sign in front of the potential, so that's why it comes in with a plus. So there's the nuclear attraction, and then there's the repulsion that you feel from all the other electrons. So this is the mean field interaction created by the density rho TFZ, the minimizer of the Thomas-Fermi potential. Now this object here, the Thomas-Fermi potential, has the following scaling. So it again has the z minus z 1/3 x, just as the density. And the whole Thomas-Fermi atom scales like z to the minus 1/3. But there's a z 4/3 in front. Right? And you actually, if you think of the leading term here, you see that the leading term has exactly that scaling, right? If I insert z to the 1/3 x down here and multiply by z 4/3 up there, then I exactly get z divided by x. So this is the scaling of the potential. Now the Thomas-Fermi potential, if you think of the Euler-Lagrange equation for the Thomas-Fermi functional when minimizing the Thomas-Fermi problem, then the absolute minimizer, if you minimize without any constraint, you don't fix integral of rho, you just minimize, then the absolute minimizer will be the neutral atom. And in that case, the Thomas-Fermi potential phi t f z of x, the Euler-Lagrange equation for this minimization can be expressed as a function, as a differential equation for the phi, and it's the equation that I wrote here. So you can show that phi will be greater than or equal to 0, and minus Laplacian phi will be equal to phi to the 3/2 times a universal constant here. Now the interesting thing about this equation is that it has two types of singularities. Now we know that, I mean, so this equation is only true away from the nucleus. At the nucleus, there will be a delta function as well added to this. But the away from the nucleus, it satisfies this. If I, however, ask the question, what type of singularity can a solution to this equation have at x equal to 0? Then there are two types of singularities. There's the Coulomb singularity, z x to the -1, where z is a parameter. It's the nuclear charge, but there's a family of singularities parameterized by a constant z. And then there is the strong, what's called the strong singularity that goes like x to the -4, and that's of course a much, I call it phi t f infinity, because what you can see is that when you look at the solutions to the Euler-Lagrange, to the minimizer for the Thomas-Fermi problem, I mean the thing for the atom, then the potential for the atom will actually converge as z goes to infinity exactly to that function here that behaves like x to the -4. So this strong singularity, and I want to emphasize it, there is a unique constant there. So there are no parameters in the strong singularity. And that is going to be extremely important in order to try to understand the structure, or the universal structure, both of Thomas-Fermi theory, but also of real atoms. So in fact, in Thomas-Fermi theory, as z goes to infinity, the Thomas-Fermi potential, I just wrote that, converges to a constant. This was this constant I had on the previous slide, times x to the -4. This is the strong singularity. Now the density will also converge. The density will converge as z goes to infinity to x to the -6. Now, I was asked before, what is the decay of the density? In Thomas-Fermi theory, the decay of the density is x to the -6. That's not the same as talking about the decay of the density of real atoms. But notice that as z goes to infinity, we get a function in the limit for the density that does not depend on z. It's like the density of an infinite atom. Of course, if I integrate x to the -6 over, if I integrate x to the -6 in the whole space, of course I get infinity. It describes the density of an atom with infinitely many electrons. But the radius of this atom, of this the neutral infinite atom, right? The thing I called R1, right? The R1 for the infinite atom, R1 TF infinity, is exactly the radius, so that when I integrate outside, I get 1. That's how I define the radius. Right? And the radius for the atoms with finite z will actually converge to the radius corresponding to the infinite atom. It will actually grow even monotonically up to this. And I will show you a picture. I will show you a graph of how the radius in Thomas-Fermi theory converges to a constant value as z goes to infinity. So even though the atom scales has sort of a characteristic scale z to the minus 1/3, it also has a characteristic scale of order 1, where the last electron of Thomas-Fermi theory lives out at order 1, whereas the bulk of the electrons, they live on z to the minus 1/3. Let me emphasize another place where you can see this universality in Thomas-Fermi theory, because you can look at the Born-Oppenheimer energy curve for the infinite diatomic molecule in Thomas-Fermi theory. So what do I mean by this? Well, think of, you have two atoms. You have an atom here at minus R with nuclear charge Z. You have another atom there at R with nuclear charge Z. You look at the neutral situation when n is equal to 2Z. And then let me calculate what I call the Born-Oppenheimer curve, which is the energy of the molecule minus the energy of the two atoms, right? I have two identical atoms here, so I'm just multiplying by 2. So written out with my notation, it's the Thomas-Fermi energy of 2Z electrons, nuclear charge ZZ, placed at R and minus R. And I'm subtracting from this the Thomas-Fermi of nuclear N equal to Z and a nuclear charge being Z. So that's the molecule minus 2 times the atom. And now I can ask what happens to this quantity, this Born-Oppenheimer curve, as a function of R as Z goes to infinity. And this will converge. So this was proved by Brazis and Lieb in 1979, that as Z goes to infinity, it converges to a curve that behaves like R to the minus 7 with a universal constant again. This universal constant is somewhat difficult to calculate, but they prove the existence of a universal constant, and so that the Born-Oppenheimer curve converges to R to the minus 7. Notice that this constant is positive. So in fact, this is an expression of what's called the no-binding theorem. The molecule has always higher energy than the atom. At least here it's said in the limit, but it's even true for every finite value of z that this thing is greater than or equal to 0. That's the Teller no-binding theorem. But as I let z go to infinity, it converges to, if you want a purely repulsive curve, a curve that has a singularity or behaves everywhere as R minus 7. So two infinite atoms in Thomas-Fermi theory were repelled by a repulsion that behaves like R minus 7. Okay, let me briefly explain how you arrive at the Hartree-Fock and the Thomas-Fermi approximations. So, so there are several steps in this, and the first step is to compare so when I don't write anything up here, I think of the full many-body problem. So I'm looking at the ground state energy of, and here I'm only doing it for atoms, again, for simplicity. And so the energy of a neutral atom minus the energy of a neutral Hartree-Fock atom. So if you only, we know that this quantity is smaller than that, because the Hartree-Fock you actually get by minimizing over a smaller families of functions than you get for the full many-body problem. So I know that this quantity is smaller than that. One can prove that the difference between the two goes like little o of z to the 5/3. Now, this was done by Pfefferman-Secco in 90, and then Bach gave a very elegant proof in 92, and Graf and myself found a different argument for the same thing. So this is actually estimating correlations. I mean, the Hartree-Fock theory is the theory where the ground state is approximated by a Slater determinant. So the difference in energy between the full many-body problem and the Hartree-Fock problem is, if you want, try to an estimate on the correlations in the atom. Having done this, one would like to now understand how to compare Hartree-Fock theory with Thomas-Fermi theory. So the first thing to do is try to control the exchange term. Now, I'm saying here that the exchange term can be calculated to big O of z 5/3. This is a little unfair. I mean, this can be done a posteriori after I have done all the other approximations that I will describe below. So essentially, for the moment, ignore the exchange term. Then we do a Thomas-Fermi approximation, and then we can come back, and when we have understood the Thomas-Fermi approximation, it turns out that one can actually calculate the exchange term to the order z to the 5/3. This was done by Dirac. But let me go to the Hartree-Fock energy without the exchange term. So this is the quantity that I wrote here in black, this thing here. So there's no, and remember I'm doing atoms here, so there's no nuclear repulsion. There's and the potential is z over x. So this was the kinetic energy, attraction to the nucleus, and electron-electron repulsion, the direct term. Now, if I add to this is the Hartree-Fock energy if I ignore the exchange term. If I add to this an expression depending on the Thomas-Fermi, this is just if I know the Thomas-Fermi density, then this is just a constant. I'm just, for simplicity, adding a constant here. I can always subtract it again. I mean, it would have been maybe nicer to write it as a subtraction on the next line, but then the next line would have been very difficult to read. What I can do now is I can complete the square between these two terms. I mean, here and there. Sort of complete the square, I can write it as a rho of the top of the Hartree-Fock minus rho of the Thomas-Fermi density. Excuse me a second, it's just.
Sure. Mm-hmm. So let us wait for Jan-Philippe to come back. Already back. Very good. So you have to unmute yourself, Jan-Philippe.
I'm sorry. Yes, yeah, I'm sorry. I had to. Somebody was knocking on my door. I complete the square, so I write this as a complete square, which means that I'm actually adding and subtracting the cross term, which is the interaction of the rho z with the rho gamma. And exactly putting this back together with this potential is going to give me the Thomas-Fermi density. If you remember, the Thomas-Fermi density was z over x minus the convolution of the Thomas-Fermi density with the Coulomb kernel. And that's exactly, when I take the trace against the gamma, the cross term in this expression. But notice that this expression is the energy of a density with itself. So this is a positive expression. So if I want to estimate the quantity I have, if I want to estimate it from below, I can simply ignore this term. And if I want to estimate it from above, well, I just have to find the trial density gamma, and I can choose a trial density gamma that will make this term very small. So in fact, it turns out that you can sort of think of this term being 0. And what you need to estimate is this quantity here. Hopefully this is self-consistent, meaning that the gamma that minimizes this quantity here will also make this term almost 0. But that's exactly where the Thomas-Fermi minimization comes in. Because what is exactly, what do you get when you minimize this expression? Well, you minimize this expression by a semi-classical calculation. And let me explain why. Because the operator that you have there, the minus Laplacian minus the Thomas-Fermi potential, if I rescale, remember z to the 1/3 x was the natural scaling. So if I rescale x to z to the minus 1/3 x, then the phi here will go to phi 1tf. Remember, there was a z 4/3, but I pulled this outside. When I rescale, I of course also scale the Laplacian by a z to the 2/3, right? But I wrote the z to the 2/3 as an h squared z minus 1/3. squared, that's z minus 2/3 times z 4/3, which is altogether the z 2/3, which is what I get when I do this rescale. Anyway, maybe you didn't follow that, but if you rescale here, you get, this is just a unitary transformation, you get this operator instead. And here, the h is like a Planck constant. It's an effective Planck constant, which is of order z to the minus 1/3. So I can analyze this problem here semi-classically. And if you do this, well, then you see that leading order semi-classics, if you remember leading order semi-classics in 3 dimensions, will behave like h to the minus 3. If I want to sum, this is summing negative eigenvalues. If I sum negative eigenvalues, I will get something of order h to the minus 3, which will be z times z 4/3 is z 7/3. So this is leading order semi-classics, or if you want, it's like Weil's law. It turns out that because of the singularity, the Coulomb singularity here, there's an added term in the semi-classics coming from the singularity, which does not appear usually in a semi-classical expression or expansion. It comes from the singularity. It's called the Scot correction because Scot was the one who discovered it in for atoms, and it has been proved to be a correct next term in an expansion by Hughes and Siedentop-Weikart, and Ivry Siegel did it for molecules. And there's even the next term, z 5/3, which was predicted by Schwinger. He included this exchange term calculation that Dirac had done, and he arrived at a correction term which was z 5/3. So Pfefferman and Secco for atoms proved this 3-term expansion z 7/3, z squared, z 5/3 with a correction which is little o of z 5/3. But let's try to understand the different scales of the atom then. So I made a profile here of the atomic density. So we have the bulk, the Thomas-Fermi bulk, which happens at z minus 1/3. There, the density is of the order z squared. If you remember, this was how the density of the Thomas-Fermi was scaling, but it's also clear that if you are at z minus 1/3 and you have to have most electrons living there so that the total number of electrons should be z, well, the volume of z minus 1/3 is of course z minus 1. I mean, radius z minus 1/3 would correspond to volume z minus 1. And therefore you need a density z squared in order to have exactly z electrons. So you have z electrons on this scale. The Scot scale, that came from the singularity. So this is something that's happening down on scale z minus 1/3, where the density is actually z cubed, of order z cubed. There are only finitely many electrons taking part of this, contributing to the Scot correction. I mean, there are infinitely many, but you get already an order z squared correction by looking only finitely many. And then when you sum them all, it converges. However, chemistry is happening out at radius 1. Right? We've already seen that we believe that the radius of an atom does not depend very much on z. Ionization energies will not depend very much on z. So we actually think that chemistry is happening out there for a large atom. And if you think of this expansion from before, if I just go back to here, the z 5/3, if we hope to continue this expansion down to understanding chemistry, which is happening here at order 1, right, I would need to improve the correction little o of z 5/3 to a big O of 1, which basically means I need to get 5 orders better in the semi-classical parameter. And that would just be the semi-classics. I also need to understand the correlations to that order. And I think actually both of these are impossible. I mean, that is not a route to trying to understand the chemical, what's happening for the atom out there. So here is an alternative approach. I want to think about universality beyond Thomas-Fermi theory. So I want to say, let's think of it in a different way. Let's not try to improve semi-classics beyond leading order semi-classics. Let's only do leading order semi-classics. But let's do it on different scales. So I will do leading order semi-classics on the Thomas-Fermi scale, which is way in there, z minus 1/3. And then I'm hoping that there's this renormalization of Thomas-Fermi. There's this strong attraction to the x minus 4 behavior, which means that I can hope to do a new semi-classical approximation on a different scale. So try to separate the inside of the atom from the outside of the atom and do semi-classics only for the outside. So trying to estimate the energy at the different scales of the atom to that relevant scale. So at a scale r of the atom, I would like to estimate the energy of that part of the atom to r to the minus 7. And the density as r to the minus 6. The total number of electrons out on this scale here would be r to the minus 3. Potential would be r minus 4. So I start inside doing Thomas-Fermi theory. Then I move to a slightly larger scale and again do leading order semi-classics. Then I go to a larger scale again, do leading order semi-classics. At every single scale, I try to understand what the density is in a way that will allow me to control the interaction with the outside, because I know enough about the inside by the leading order semi-classics I did. And this procedure actually works for Hartree-Fock theory. Here I wrote only because I don't know how to make it work for Schrödinger theory, because in Schrödinger theory, I do not know how to separate the different, the inside from the outside. I do not know how to control the correlation energies the way I can do it in Hartree-Fock theory. But here is then a universality theorem in Hartree-Fock theory. This is something I proved in 2003. So if you integrate the Thomas-Fermi, the Hartree-Fock density outside a radius r, so fix r, ask how many electrons do I have outside a radius r, and let me take the limit z going to infinity. Unfortunately, I cannot prove that it has a limit, or maybe it's not unfortunate because maybe it doesn't have a limit. But I can find, so I put the lines in here. So I talk about the lim inf and the lim sup. I can calculate the lim inf, or not, I mean, I can show that there is an upper and lower bounds so that I have lim inf and lim sup of this quantity. And what you can show is that as r goes to 0, both the lim inf and the lim sup will have the same asymptotic behavior. So I have the universal behavior of Thomas-Fermi theory you find it again in Hartree-Fock theory by going to the infinite Hartree-Fock atom, at least lim sup, lim inf, infinite Hartree-Fock atom, and then looking at the singularity as r goes to 0, and you will see that it actually has a very precise asymptotic behavior in Hartree-Fock theory. And using this behavior, I was able to prove the ionization at both upper and lower bounds on the ionization energy, and an upper bound on the maximal ionization, but only in Hartree-Fock theory.
So Jan-Philippe, there is a question.
Yes.
For how many length scales in that iterative process?
Infinitely many, in a sense, right? because every time, I mean, you have to get out to order 1, and every time you, I mean, in principle, I guess it's as z goes to infinity, it's an infinite number of steps that you have to do, because you gain only a little bit in every single iteration. Right? But that may not be the right way of looking at it. I think of it sort of as a continuous. It's more a little. It's more like a renormalization scheme. It's more like a continuous scale that you move out to scales of order 1.
And is there some sense of renormalization group?
I don't know if there really is a renormalization group. I mean, I mean, it's not like you integrate out certain high energies or anything, but of course you can always think of rescaling the r to being of order 1. So in a sense, there is a fixed point. The fixed point is the x to the minus 4. Right? So, but if I don't know if I can really say that there is a renormalization group.
Fixed point of what? Of what transformation?
that's what I'm saying. There is no transformation, but the Thomas-Fermi potentials phi z converge to the x to the minus 4. Right? As z goes to infinity, the phi z converges to x to the minus 4. So if you want the behavior of the Thomas-Fermi potential, the r minus 4 here, and at every single scale, you show that it actually behaves like this universal constant times the r to the minus 4. So it may not be a fixed point or of a transformation. It's the fact that this Thomas-Fermi potential has a unique strong singularity. So you can show that any solution to the Thomas-Fermi potential will actually behave like this in a certain range of scales. So this leads me to actually make a quantitative ionization conjecture. So in fact, for the real atom, I believe that if you integrate the density outside a radius r and you multiply by r cubed, so take the limit as z goes to infinity, take r cubed, let r go to 0, then you should converge to this number that you're getting in Thomas-Fermi theory. So this would be the value in Thomas-Fermi theory. In Hartree-Fock theory, I was able to prove this, but I believe it's actually also true for full quantum mechanics, full many-body quantum mechanics, and it expresses this universality and the ionization conjecture in a quantitative way, right? Because it gives us a quantity that even after letting z going to infinity is of order 1. This quantity here, as z goes to infinity, is order 1. I don't know what it is, but I know what its asymptotic is as r goes to 0. The reason I need r going to 0, if I go back here, is that I need to dive into the atom far enough that I have enough electrons that I can do a semi-classical approximation. If I'm all the way out at order 1, then there are only there's only one electron. That's not enough to do semi-classics. So that's why on the scale of order 1, you have to go to short scales. And I also believe that the universality of Born-Oppenheimer curve that we saw in Thomas-Fermi theory holds as well for a molecule. So as r goes to 0, if I do this same thing as I did in Thomas-Fermi theory, I calculate the repulsive curve for real atoms, let z go to infinity, multiply by r to the 7, let r go to 0, you will get this constant that in the case of Thomas-Fermi theory was proven by Brézis and Lieb. So this was proved by Brézis and Lieb in Thomas-Fermi theory. In a recent paper with a PhD student, we actually proved this, not for Hartree-Fock theory. We couldn't actually get it to work for Hartree-Fock theory. We had to look at a somewhat simplified model where we removed the exchange term. So in Hartree-Fock theory, without the exchange term, we were again able to prove this quantity. So let me finish by just comparing this quantitative ionization conjecture with these experimental values for the radius of an atom and also with Hartree-Fock calculation. So let me go back to this thing that I started with, the periodic table where we had drawings of the radii, I mean the size of atoms. And let me look at the first group, I mean the alkali atoms. For those, as I said, Bragg in 20 and Slater later in 64 collected these empirical radii. And the dotted curve here is the one by these numbers here are the ones that Bragg found. The diamond numbers up here are the ones that Slater found. So you see they don't quite agree because they looked at different compounds, and as we already discussed, it's not a precise value that you're getting. It depends on which compounds you're looking at. So you find different. You certainly find different values. The red curve is the Thomas-Fermi curve for radius 1. So what I was saying, sorry. What I was saying before was that to define the radius mathematically, you may want to say it's where you have only one electron. Now for the alkali, remember the alkali atoms are the ones where you have a noble gas and you add one more electron. So it's one more electron in the outer shell. So it's natural to say that the radius is that you think of the atom as a hard Fermi core corresponding to the noble gas, and then you have one more electron moving around there. So it's natural to try to say that it's the R1 that corresponds to the radius. But this is somewhat ad hoc. In any case, I calculated the Thomas-Fermi curve for the radius 1, meaning out to having only one electrons. And that's the red curve that you see there. And I'm just very surprised that you give not only qualitatively right behavior, that the radius grows as you go down the group, you actually even in some cases get numerically exactly the value that either Mr. Slater or Mr. Bragg, found here, and here actually the same value as they both found. So I think this gives a very nice prediction of how the radius of an atom behaves down the group. Now, if you go to infinity, if you let Z go out to infinity, you will eventually end up with a very large radius, which is 390 picometers. And the last thing I wanted to show you was the Born-Oppenheimer curve. So to understand this prediction, so together with two chemists, Gilka and Taylor, that were good at doing Hartree-Fock calculations. In fact, they knew how to work with this program called Dalton. We calculated the Born-Oppenheimer curve in Hartree-Fock theory for a certain number of elements. But they had to change the program because I wanted to look at the very short distance behavior, right? Much shorter than the equilibrium point. So one had to readjust a little bit the program, which the chemists found to be a challenge. An interesting challenge, which was lucky for me because they went in and did it. And here we actually subtracted off the nuclear-nuclear repulsion. I mean, the nuclear-nuclear repulsion is something that's known. It's the same in all theories, Thomas-Fermi or whatever. So what we did was we calculated the Born-Oppenheimer curve in Hartree-Fock theory. We rescaled it according to the Thomas-Fermi scaling, Z 1/3, and over here the Z minus 7/3. And then we plotted all these atoms, these diatomic atoms, so helium, helium, lithium, lithium, and so on. We plotted them in the same diagram. And later on, I asked a student of mine, Samoilo, that had done the proof with Hartree-Fock theory before, to actually calculate it in Thomas-Fermi theory. It's not an entirely trivial calculation because the diatomic molecule in Hartree-Fock theory, you still have to solve the PDE, but you see the curve here. Let me actually enlarge it a little bit. So you see the numerical values, and you're comparing them here with the Thomas-Fermi curve, and there's a pretty high accuracy of these two. So this prediction that the Thomas-Fermi is actually better than its reputation, I think is there's a lot of good evidence for that, both numerically and also experimentally in the curve that I had right there. So that's all I wanted to tell you about the universality of atoms, and I hope I have interested maybe some young people in attacking this problem. I think it's a really challenging problem to try to understand this for the full many-body atomic description. So thanks a lot for your attention.
Thank you very much, Jan-Philippe. I'm going to unmute everybody so we can upload Jan-Philippe. So let me mute everybody back. And are there questions? So you can ask questions directly by unmuting yourself and asking the question to Jan-Philippe, or to write something in the chat, in which case I would read it to Jan-Philippe. Are there questions?
Can I ask real quick?
Sure, Jan.
So you showed in the previous slide how Thomas-Fermi works very well for alkali atoms, but as you see in the periodic table, alkali atoms seem to be rather peculiar. Do you expect that to see anything good about Thomas-Fermi and radii for other atoms that are not in the first column of the periodic table?
Jan-Philipp, we do not hear you. Perhaps you have.
Sorry. Yes. Thanks a lot, Jan. So the question is, what I did was in the first group, I chose the R1, right? I chose to compare these experimental radii with what you get if you choose the definition R1, meaning the radius so that there's one electron outside. Now, if you go to group 2, that's probably not the right definition because there are 2 electrons running around. I mean, you've added 2 electrons to the noble gases. So I actually tested it a little bit. I tried to define it R1 or R2, but R2 then gave a radius that was too small. R1 gave a radius that was too big. So I played a little bit with it, and it turned out that actually 1.6 was a pretty good fit with the experimental radii. But again, no, I'm not expecting that I will be able to predict. This was somewhat ad hoc. The first group was by far the easiest to think about because there's sort of a clear definition of one added electron to the hard core, if you want the Fermi gas that you would get for the noble gases.
I have a question concerning this table. Why noble gases have gaps?
Well, I mean, there are not that many compounds with noble gases, I guess, right? So I'm even surprised that there are anything in this column. But
so if there is nothing in some places, it means that you cannot define experimentally the radius.
That's right. You don't have enough data to define the radius experimentally. Actually, if you go, so I took this from Web Elements, and this table has changed a little. It's been time dependent. At some point, there were actually things in here as well, but then they were removed again. So I don't. I think that I think they can. It must be very difficult to predict the radius of a noble gas using this bond, the bond definition.
Are there other questions?
I'd like to ask a question. Maybe it's a little naive. I mean, maybe it's kind of nonsensical, is what I mean. It's there's somehow this universal behavior of 1/r⁷ as the repulsion that you predict based on Thomas-Fermi. And I mean, I remember back from chemistry classes that Leonard Jones has a 1/r⁴, which is supposed to be something universal somehow. I never really understood exactly why there was a 1/r⁴, and I wonder what the relation is there. Why?
Okay, so I also never understood where the 1/r⁴ really came from. I think there was this. I had the feeling is just to find something which is very repulsive. Now, I should say that these are very different scales, though, because maybe this is, you can best see it from this curve here. The r-7 is you have to understand. I talk about the r-7 as a singularity near 0, but this is only for the infinite atom. I mean, you take an infinite atom, and then you will see this repulsive curve, r-7. But you might ask yourself, where does this r-7 actually kick in? So what is the scale for real atoms? And that scale is essentially the same as the scale where the atom starts having a radius corresponding to the, see, this is the radius of the infinite Thomas-Fermi atom. right? So it's almost 400. It's nearly twice the radius that you see here. I mean, you have to go very, very out to very, very high Z before you, for an atom, come close to this 390. In the same way, in order to see the R-7, you have to let Z be extremely big. So it's not something, R-7 is actually not something you will see in real atoms. It's something that was useful in order to make a mathematical statement. And that's why I also thought it was interesting to actually do the calculation with real Thomas-Fermi, with the real Thomas-Fermi, and compare Hartree-Fock to real Thomas-Fermi. So the R-12 is something that's happening on a scale which is short compared to the sort of the standard atomic scales. What I'm talking about, the R-7, is actually on that scale something that's very, very long, except we haven't seen it yet because you have to let Z go to infinity first. And the Z going to infinity, right? I mean, remember this, the Z minus 1, or let me put it this way, the R to the -1 over 12 is a scale that's short compared to the Z minus 1/3, to the Thomas-Fermi scale, right? Whereas the R-7 is a scale that's very long compared to the Z minus 1/3. So I think for real atoms and molecules, in the range of real atoms and molecules, you will not see this R-7. I still believe it's there if you could go to the infinite large atom, even quantum many-body atom, right? But it was just a way to quantify the ionization conjecture, because I have no way of actually doing good estimates at finite Z. There, one had to rely on the numerical evidence.
Thanks.
Thank you. Further questions? If no other questions, let us thank Jan-Philipp again. Thank you very much.